Okay, are there any questions before we move forward on what was done last hour? So we're trying to extract as much as we can for the sake of engineering applications from the ideal gas law, and this formulation of the approximate gas formation volume factor does allow us to do something useful. It allows us to establish that the pressure dependence of gas formation volume factor is 1 over P, which is a good reason that when plotting graphically the data for a field, BG versus pressure, it's a much better idea to plot the inverse function, okay? Because the graphical representation of if you plot BG, and basically you get this thing that goes really high at low pressures, and then it comes down like this, and you're really interested for the most part in the numbers here, and you don't get a very good resolution because you're only using a very small part of the y-axis, and it's very nonlinear. This might be initial reservoir pressure, and so what's a much better idea for graphical representation of the measured data or calculations is to plot little bg, which is an exact straight line going through 0, 0. For ideal gas law, it's a straight line continuously. But for a real gas, what will happen is that this will start deviating at some point, something like that. So this is ideal gas, and this is a real gas. But the point is that both of those will be relatively linear in terms of pressure. So it's just a much better graphical way to present these numbers. So these numbers will be like in the magnitude 100, 200, and 300, as I was telling you about. And this unit would be something like this or this. Okay, so that's what we got out of the ideal gas law in terms of this volume factor for gas. If you want a little bit of a challenge, if this seemed to be very trivial, the whole exercise, you might challenge yourself with coming up with the expression for BG if we relax this second assumption. Okay, this second assumption here. If we relax this assumption here, and instead we just define a term FG as how much of the initial gas we start with actually ends up being surface gas. Okay? And what you'll find is that this term F of G will in fact be a pressure dependent function. It's because this, okay, so if you can come up with this is FG, that's basically a so you'll have a new variable in the equation for BG that takes into account for the fact that how much of the original gas becomes surface gas depends on how much liquid it condenses out, and how much liquid it condenses out depends what the reservoir pressure and temperature are. Okay, so that's that might be a challenge that you can take on. Okay. The next thing I want to do.
I'm sorry.
Yes.
I made a mistake. The second graph, it should be standard cubic feet for cubic feet.
Yeah, that's right. Thank you. Thank you. Thanks. Let's see. Yeah. Okay. So this, the next application of this equation, and probably the most important one, of the ideal gas law, is to give a means to convert standard volumes or surface volumes to moles, or from moles to surface volume, surface gas volumes. That translation from moles to surface gas volumes back and forth goes on all the time in different engineering applications. So the first thing I want to make comment about is that gas volumes in general, okay? Gas volumes reported and measured and used are, I won't say always, but most often at standard conditions, okay? Even if we're making the measurement at 100 bar, the calculations that you make will not give you the gas volume at 100 bar. It'll translate the measurements at 100 bar to standard cubic meters or standard cubic feet. So you almost always see gas volumes expressed at these standard conditions. Okay? And in many situations, we want to use molar amounts instead of gas volumes, or vice versa. So the translation from gas volumes to moles, or vice versa, is common in all different types of engineering. And because of that, we're basically going to always be translating, because of this first point, we're almost always going to be translating from surface standard condition gas volumes to moles and back and forth. And there's these two numbers that one of them you should remember, just burn it into your brain. Basically, is the one is 379 approximately standard cubic feet per pound mole, and the other is 23.60, I think it's around 68 standard cubic meters per kilogram mole. Okay? And then you guys probably learned a number in high school, at least I did, believe it or not, in Oklahoma, where, you know, grams and cubic centimeters were almost considered communist. And when I grew up, communists were or dealt with in a bad way in the United States. Even I remember learning in my chemistry class about some number of liters of gas per mole of substance, gram mole of substance. Does anybody remember that number from high school? 22.4? It's what you find in most chemistry textbooks. So there's this 22.4 liters per gram mole, I believe. Actually, the way this is, the SI unit for, well, first of all, they write it this way, but that's the same as liter per, what I use is gram mole, because I always put the mass unit associated with the quantity of moles. Okay? And I think liter is decimeter cubed. So I guess the formal SI would be, I think it's, isn't that correct? Yeah. Okay. But basically liters per gram mole. So what I want you to now do, and I'll have to give you 3 numbers to do this, or 2 numbers to do this. I want you to do these calculations yourself, figure it out. Where does the 379 come from? Where does the 23.60, I never remember the number, 69, whatever, and the 22.4 come from? And I'm going to give you numbers. This is 10.73146, and that's using pressure unit of PSIA, temperature unit of Rankine, volume in cubic feet, and mass unit of pound. So it'll be pound moles. And the universal gas constant for what's the SI universal gas constant?
8314.
8314. Okay. Anybody disagree? Huh? Times 1,000?
But it's 8,314.
Okay, 8,314. Do you mean it's 8,314 times 1,000? Or, yeah? So like 8 million?
No, 8,000.
8,003. Okay, 8,314. Does anybody disagree? I disagree. I don't even know my units.
Kelvin.
Okay.
Kelvin Pascal.
Okay.
Like kilogram. Kilogram mole.
Okay, just give me the 4 units you think it. Okay, I'm just going to make a point out of this because you may be right, but you may be wrong. You may be right, but you could be wrong. That's the life. That's my motto in life. I could be right, but I might be wrong. So we got 83.114. Don't look at your book. What units do you have for pressure for that?
Pascal.
Pascal? And then temperature, Kelvin? Cubic meters?
Kilogram mole.
And kilogram mole. Okay. Anybody? Okay. So what we're going to do is check that because I don't know it. The other one I do know, but I don't know that one. So we're going to check that in the monograph, which is not here. And why not? I don't know. By the way, I put this on the miscellaneous here. It's supposed to be there. There it is. So this monograph, it's not there. Let's see here. Got to be here somewhere. Okay. Well, I'm going to do it a little bit easier. It's Appendix A. Okay, In Appendix A, there's kind of a table specially for getting the right universal gas constant for different units. So you can pick PSI, cubic feet, Rankine, and pound mass for moles, and that's this 10.315 number. And then if we go for Pascal, cubic meter, Kelvin, and kilogram, we've got the 8314 number that he gave. Okay, so 0.3. But if you don't remember those numbers, and like in high school, you probably learned Pascal, cubic meter, maybe Kelvin, and kilogram is the same thing. 8314. Oh, I'm sorry. Yeah, you use Pascal. And then what most of the petroleum engineering companies use, like Statoil and Canadian companies, they'll often use bar and cubic meters. So they'll often use these units here, in which case your number is 0.083143. So if you want to use bar instead of Pascal. Okay. So you basically need two of these numbers with units, and with those numbers you should be able to make a calculation that verifies these three numbers as being approximately right, very right, or we need some adjustment. Okay, and we do that all from this ideal gas law. Okay. I'm not quite sure what you mean, but if you have 1 pound, if you have 362 pound moles given by some engineering company, and you want to know how many standard cubic feet it has, that's the number you would use to convert. And if you had given by another engineering company so many standard cubic meters, and you needed for some reason kilogram moles of that amount, then you would divide by this number. So these are kind of numbers that we use all the time. And the only number I always remember is the 379, and it's 23 point, I think, 6 something. And I just want you to check these numbers. And these, we're talking at standard conditions here. And then the pressure is well defined. Or but we do have some alternatives here. Sometimes countries or different, not petroleum engineering societies, but other societies may use 20 degrees C, and some of them I think maybe even use 25 degrees C, but at least you can use 60 degrees Fahrenheit because this is the Society of Petroleum Engineers standard. So this might be other societies or countries. Okay. These should be the way you calculate them.
Isn't it supposed to be 10 to the power of 5?
Yes, it is. I'm sorry. Thanks. See, I might be wrong. I could be right. I could be right. I might be wrong. It's always just, you never know. Thanks. 10 to the 5th Pascal in a bar. There's also a lot of alcohol in a bar usually, certainly soda water. So. That's as close as you're going to get to jokes from me, afraid. It's going to be a long semester. So what did we come up with here for this first number? Anybody get all those numbers punched into your little telephone? Okay, that's good. Took me at least a decade or so before I did remember it almost right, 2368. And then for the other one? 379. That's good. Point. Okay, 0.5. So, all right. Okay. So these are kind of the two numbers you need. One of them you can keep in your mind and know that you can use it. And you can use it for any gas. Methane, CO2, doesn't matter what gas. Gas, any mixture behaving as an ideal gas at standard conditions, which they pretty much all do at 1 atmosphere. What about this 22.4? Did anybody figure that out? Do you remember what your book, the book that you had in high school, either used 20C or 25C probably. And if you use one of those two numbers, you should get the 22.4 number. Huh? It's 0 degrees C. Did you check that now, or do you? Okay. I'm glad you don't remember from high school, because that would be spooky. Okay, 0 degrees C. Okay. That's associated with, that's kind of cold. Not in Norway. But. Okay? Now, before we round off this hour, most of you think, well, this is like crazy to wake up in the morning and come to lecture like this. We're just doing like refinement of high school stuff, and that's kind of true. But petroleum engineers sometimes, for reasons I can't get into quite yet, but sometimes we actually want to convert stock tank barrels into equivalent, what if it was surface gas? They call it a gas equivalent of oil. Okay? And I'm not going to go into the reasons why we want to use that or why we do that, but it's sometimes done. So that you've got this certain amount of oil, stock tank oil, I'll write it like this, or stock tank oil like that. And we want to know what is the equivalent of this as a stock tank gas, as a surface gas. Okay? Okay. Now, how might we go about doing that? Any suggestions? Any bad suggestions? I mean, everybody's got to have a bad suggestion out there. I mean, any suggestions? What we want to do is we want to get some kind of equivalent surface gas Yeah, so what if we convert this volume into moles of stock tank oil? And then we just stamp it with that number, 23.68 or 379. Okay? So we've got to convert volume to moles, and then we multiply by this RTSC over PSC, which is what we've called that. So we basically want to multiply by that number there. But first we have to convert from volume to moles. And to do that, How do we do that? We can measure the density of the oil. That's pretty straightforward, right? And if we multiply by the density of that oil, that doesn't give us kilogram moles. It gives us kilograms, right? But at least we've gone from cubic meters to kilograms by doing this. But then we need another quantity of the oil, of the surface oil, to convert that kilograms to kilogram moles. Anybody remember what that is? The molar mass, they call it in the SI, or molecular weight in Oklahoma. Okay? Molecular weight or molar mass. That's density. This is in standard cubic meters. And then if we use the molecular weight or the molar mass, that's giving how many kilograms per kilogram mole. So we'd have to measure that or estimate that from a correlation. And this whole thing, because units will cancel out, we'll basically get rid of the cubic meters here, we get rid of the kilograms there, and we're left with kilogram moles here. And once we take that, we can use this magic number 23.68, which gives a standard ideal volume cubic meter gas per kilogram mole. Right? That's the units of that number there. And we can cancel out the kilogram moles. So we end up with what we wanted was this equivalent standard cubic meter. This is a green standard cubic meter because it's oil. We've now converted it over to this red standard cubic meter, which is a fictitious, theoretical, fictitious standard cubic meter of ideal gas equivalent. So that's a process that we'll do sometimes in some of the exercises during the course. But basically, this is being done either by you with your calculator or behind the scenes with some program you're using. Okay? So that's gas equivalent of stock tank oil. And then there's going to be one final strange thing, conversion we're going to do before we retire today. And that has to do with what governments and authorities and newspapers, when they report a new discovery in Norway, even if it's a gas discovery. Oh, we found a new big gas field. What they will often do is give you the amount of what they think is there in what's called BOE. Has anybody heard of BOE? Barrels of oil equivalent. So then they're converting the gas to something as if it was a barrel of oil. Okay? A lot of weird stuff going on here. So I'm just going to talk a little bit about barrel of oil equivalent. Because it's really used a lot in, particularly in the media. It's written BOE. Its unit is a barrel. when they do this, they're basically, what they're trying to do is that they're trying to put surface gas and surface oil on an energy basis. Not a volumetric basis. Okay? So it's kind of an energy unit, in a way, at least approximately. And on an energy basis, there are about 6,000 standard cubic feet. No, that's not right. I'm going to mess this up for sure. Yeah, I think it's right. Yep. In energy of a surface gas is approximately equal to the energy of one stock tank barrel. In terms of energy. British thermal units or joules or whatever, energy or unit, depends on the quality of the oil and the quality of the gas. But I think the general conversion is approximately 6,000. Okay. So, for example, just to kind of give you an example, we've got Troll gas. These are the big North Sea fields, okay? Troll gas is the biggest North Sea field. You've got Ormen Lange, which most of you grew up with. When you were alive, it was discovered and it was developed a few years back, and so this is approximately 45 10 to the 12th standard cubic feet. They call this TCF. Trillion is 10 to the 12th. Not an SI, but in field units. And Ormen Lange is about 10 TCF. And the largest gas field in the world is in Qatar. It's not only, it's basically it's gas, and this is called the North Field in Qatar as they call it, and it's about 900, they say, I'm not sure they really know, TCF, okay? That should actually be a capital T there, I'm sorry. Okay, so the question is, what is the equivalent barrels of oil equivalent for these? Just so we have kind of a feeling. And all you have to do is divide the standard cubic feet by 6,000, right? So can somebody help me do that? Well, this is going to be easy. Well, not easy. I'll still let somebody do it, because 900 10 to the 12th divided by 6,000. That would be the same as 900 10 to the 9th divided by 6. 900 divided, there we go, 150 billion, I think, isn't it? Is that right? And Troll? I have to be a little bit careful here. You can give me these numbers.
1 and 6.
Huh?
166.
166?
1.66.
Yeah, that makes it 1.67 billion. And Ormen Lange, that would be
Oh no, actually, yeah, it was Orman 167.
Okay. And Troll?
725.
Okay. No, I think that's it. Let's see, BOE conversion. I'm just going to double check. I think it's 6,000. 6,000 cubic feet. Yeah, okay, typical guess. All right. So, the largest oil field in Norway. Now you have to realize that the dollar per barrel value, the dollar per real barrels is about 110 today. But the dollars per barrel oil equivalent for gas is about 1/6 of that. Depends where you are in the world, but it's a lot less. A fifth, a sixth, a seventh of that. So it's much less. You get dollars per barrel. But if we forget about that, just energy. The largest oil field in Norway is around 8 billion barrels. Statfjord. Ekofisk, 6 billion barrels. So the Troll gas contains, of course the Troll also contains oil, but if we forget that, just the gas part of Troll contains about the same energy equivalent as Statfjord contains an energy equivalent of its oil. And a big oil field in the North Sea of 1.7 billion barrels would be big, as is 10 trillion. So this is a way of converting. And the world's largest oil field, which is Ghawar in Saudi Arabia, we'll just go look there and see how big it's supposed to be. GH Ghawar oil field. I'm sure there's a Wikipedia here. It's some 280 kilometers long by 30 kilometers. Let's see here if they put the amount of oil there. Let's see here.
Scroll up on the right side of the table.
Oh, okay. Oil in place. 71 billion barrels. 71. Of course, that can't really be right. That's production, because the claim that they've already produced 65 billion barrels originally exceeded 100 billion barrels. Okay, but if you look at that here, it's less than the energy equivalence of the North Field. In other words, the North Field contains more energy in a sense than the Ghawar field. So anyway, this is just something for you to realize, that people talk about energy equivalents, barrels of oil equivalent. So with that, we'll leave that, and I'll see you tomorrow at noon, maybe.